Next, let us mesh the model. If we look carefully at the geometry at hand, we see that it has parts of different sizes and having different features. So if we use a default element size, the mesh may not capture these different features and geometrical details adequately. Based on the average dimensions of the parts, let's use an element size of 7.5 e to the power minus 3 meter or 7.5 millimeters for the overall mesh. If we input the element size and point the cursor anywhere on the body, we see a small circle accompanying the cursor. That circle is an approximate representation of an element of size 7.5 millimeters. So this is a quick way to decide whether or not the element size that we have chosen will give us a fine enough mesh or not through visual inspection. If we reduce the element size, the size of the circle will reduce correspondingly. So an element of size 2.5 millimeters will be approximately of the size indicated by the circle here. Since this seems to be a very fine mesh, which will increase the computational cost, let us go back to the element size of 7.5 millimeters or 7.5 e to the power minus 3 meters. Next, since the bolts are smaller in size, we wish to have a finer mesh on them so that their features are captured adequately. So right-click on Mesh and insert sizing. For the scoping method, let's use named selection and select bolts from the list of named selections. For the bolts, let's use a smaller element size of 5 e to the power minus 3 meters or 5 millimeters. Next, let's hide the bolts. Now we also want a finer mesh for the imprints of the bolt heads to ensure proper contact engagement between the bolt heads and the mating components. Let's align the view to the XY plane. We can go to the Display tab and choose the display to be wireframe. Since we need to get a finer mesh on some of these faces, right-click on Mesh and insert sizing. Choose Face Selection and change the select mode to Box Select. Select the faces where we wish to get a finer mesh. Be sure to press the Control button while selecting multiple faces. Let's align the view to YZ plane and select the other bolt head imprints. We can rotate the view to make sure that all the required faces are selected. Then we can click on Apply in the scoping method. Let's use an element size of 5 e to the power minus 3 meters or 5 millimeters for these surfaces as well. Let's go to the display and switch back to shaded exterior and edges. Also, let's right-click and show all bodies. Now that we have specified the element size on various parts and features, we can right-click on Mesh and choose Generate Mesh. So by default, we use the tetrahedral elements for the mesh, and we can see that the mesh on the bolts is fine enough to capture its geometrical features. Now the next step is to set up the case, that is, applying the bolt pretension, the operational forces, and then solving the system. First, let's go to Analysis Settings. Since we have bolted joints where bolt pretension is applied, we need to have two steps. The bolt pretension is applied in step 1, and then in second step, the bolts are locked and operational loads are applied. So define the number of steps to be 2. First, let's apply the preload on bolts. So right-click on Static Structural System and insert bolt pretension. Hide all parts other than the 4 bolts. So now we will apply bolt pretension. To avoid the slicing plane from passing through the bonded contact region, we will scope it to the bolt shank face. So select one shank face and say apply in the scope. Don't forget to lock the bolt pretension in the second step when operational loads are being applied. Let's apply a bolt preload of 100 Newton in step 1. Next, we use the Object Generator tool from Automation tab to create bolt pretension objects for other bolts as well and group all of them together. Now we want to apply fixed support. Right-click on the Static Structural System and choose Insert Fixed Support. Select the back surface of the wall and say Apply. Next, let's apply a force on the inner surface of the bearing. Let's say we want to define the force by components and apply a force of 200 newtons in positive x direction. Now this is a problem involving bolted joints and bolt pretension. So make sure that the force applied in the first step is 0 and it is 200 newtons in the second step, since the first step is reserved for applying bolt pretension, and applying operational loads on the assembly simultaneously in the first step will lead to wrong solutions. Apart from this, since we have used frictional contacts between certain pairs of surfaces, we have non-linear contacts to resolve in the first step. To help improve the convergence in the first step, we will define a certain number of sub-steps in the first step. Since we are going to define the number of sub-steps we want the solver to use, let's set auto time stepping to off. Let's define the number of sub-steps to be 5. For step 2, let's keep the auto time stepping to be program controlled. This completes the setup for the model and we are ready to solve it. But before solving the case, let us do one final check to make sure that all the contacts have been defined correctly. Right-click on Connections and choose Insert Contact tool. We can right-click on the initial information and say Generate Initial Contact Results. Now, let us check the initial contact information. In the worksheet, we observe that 4 bonded contacts are highlighted in red and 4 frictional contacts are highlighted in yellow. According to the legend, the status of the contacts highlighted in yellow and red are open or near open. The contacts highlighted in red are supposed to be closed, but their status is far open. Also, there are no contacting elements for these contacts. So these 4 contacts are a cause of concern and need to be fixed before we can proceed with solving the model. To resolve this, we will go to one of the 4 contacts, select it, right-click and go to Selected Item in Tree. The 4 contacts between the bolt threads and the respective slots are the ones that were highlighted in the initial information worksheet. To resolve this issue and close the gap between contacting surfaces, we will increase the pinball radius. The pinball radius should be larger than the gap between 2 faces for detecting contacts between them. To decide the appropriate pinball radius, first let's measure the clearance between the contacting surfaces. To do this, select the body of the bolt, right-click and select Hide All Other Bodies. Then using the select edge tool, we see that the radius of the threaded portion of the bolt is 1.4 e to the power minus 2 meters or 14 millimeters, and the slot radius, which is equal to the radius of the bolt shank, is 1.6 e to the power minus 2 meters or 16 millimeters. So that means there is a gap of 2 millimeters between the threaded portion of the bolt and the slot. Due to mesh discretization, the surfaces are not exactly cylindrical but are in fact faceted. Due to this reason, the pinball radius needs to be higher than 2 millimeters in order to allow some tolerance for these faceted surfaces. So select the 4 contacts. Under Advanced, go to the pinball region and select Radius and define a pinball radius of 4 e to the power minus 3 meter or 4 millimeters. Next, let's move on to the frictional contacts that were highlighted in yellow in the initial information worksheet. Since the contact area between the bearings and the brackets is quite large, in order to get accurate results, we need to ensure proper initial contact between these two contact pairs. If we zoom in, we can see this gap clearly. In order to close this initial gap, we go to the geometric modification, and for the interface treatment, we select Adjust to Touch. So this closes the small gap between the bearing and the brackets and ensures that sufficient contact is established between the bearing and the two brackets. Then, let's generate the initial contact information again. Now we see that the 4 bonded contacts are closed as indicated by the orange highlighting, and there are sufficient number of elements in contact with each other. Also, the status for contact pairs between the bearing and the two brackets is now closed. So in this way, we can change the pinball radius and use the Adjust to Touch option to resolve the contact pairs that weren't closed initially. So with this issue resolved, we can move on to solving the system. Under the Home or Solution tab, specify the number of cores in the machine that you want to use to solve the system. Here, we will use 4 cores. Then right-click on Solution and choose Solve. Once the system has been solved, we can check the results. Let's first look at the total deformation. We can animate the results to see the deformation of the assembly at different times. Since the deformation values are very small, we can increase the scaling factor by which the deformation is enhanced so as to better visualize the deformation. We see that the force applied on the bearing in the positive x direction lifts up the bracket from the wall. Another important result that we want to check is the contact status. So right-click on Solution and Insert Contact tool. Then right-click and say Evaluate all results. When we click on Status, we can check the contact status for all the contact pairs. At the end of the second time step, that is at time 2 seconds, since the bracket lifts up from the wall, we see that the status is sticking or sliding at the top edge of the bracket and the wall, but everywhere else the status is near as indicated by the yellow color. We also see that the status of the threaded portion of the bolts is sticking, which is expected since we have a bonded contact in these regions. In case of the bearing, the force in positive x direction leads to a sticking status between the bearing and the brackets in the positive x direction. Now let's check what the contact status is at the end of the first step in which bolt preload has been applied. So change the display time to 1 second. We can also change the scaling factor to 1 or true scale. We see that regions close to the bolt heads have a sticking or sliding status, which confirms that the bolt preload has been applied correctly and sufficient contact has been established between the bolt and the mating components. So now you can follow the steps in this video and try to solve the system for yourself using the geometry and the archive project files provided with this workshop.